Double-slit experiment in modern physics. The double-slit experiment demonstrates that light and matter can satisfy the seemingly incongruous classical definitions for both waves and particles, which is considered evidence for the fundamentally probabilistic nature of quantum mechanics. This type of experiment was first performed by Thomas Young in 1801, as a demonstration of the wave behavior of visible light. At that time it was thought that light consisted of either waves or particles, with photons or matter, like electrons, produce the beginning of modern physics. About 100 years later, an interference pattern when two slits are, it was realized that light could in fact show both wave and used particle characteristics. In 1927, Davison and Germer and, independently, George Paget Thomson and Alexander Reid demonstrated that electrons show the same behavior, which was later extended to atoms and molecules. 234 Thomas Young's experiment with light was part of classical physics long before the development of quantum mechanics, and the light from a green laser passing through two slits 0.4 mm wide and 0.1 mm apart concept of wave-particle duality. He believed it demonstrated that Christian Huygens' wave theory of light was correct, and his experiment is sometimes referred to as Young's experiment 5 or Young's slits 6. The experiment belongs to a general class of double-path experiments, in which a wave is split into two separate waves. The wave is typically made of many photons and better referred to as a wave front, not to be confused with the wave properties of the individual photon, that later combine into a single wave. Changes in the path lengths of both waves result in a phase shift, creating an interference pattern. Another version is the Mach-Zehnder interferometer, which splits the beam with a beam splitter. In the basic version of this experiment, a coherent light source, such as a laser beam, illuminates a plate pierced by two parallel slits, and the light passing through the slits is observed on a screen behind the plate. 7-8 The wave nature of light causes the light waves passing through the two slits to interfere, producing bright and dark bands on the screen, a result that would not be expected if light consisted of classical particles. 7-9 However, the light is always found to be absorbed at the screen at discrete points, as individual particles, not waves. The interference pattern appears via the varying density of these particle hits on the screen. 10 Furthermore, versions of the experiment that include detectors at the slits find that each detected photon passes through one slit, as would a classical particle, and not through both slits, as would a wave. 11 12 13 14 15 However, such experiments demonstrate that particles do not form the interference pattern if one detects which slit they pass through. These results demonstrate the principle of wave-particle duality. 16-17 Other atomic scale entities, such as electrons, are found to exhibit the same behavior when fired towards a double slit. 8 Additionally, the detection of individual discrete impacts is observed to be inherently probabilistic, which is inexplicable using classical mechanics. 8 The experiment can be done with entities much larger than electrons and photons, although it becomes more difficult as size increases. The largest entities for which the double-slit experiment has been performed were molecules that each comprised 2,000 atoms, whose total mass was 25,000 atomic mass units. 18 The double-slit experiment, and its variations, has become a classic for its clarity in expressing the central puzzles of quantum mechanics. Because it demonstrates the fundamental limitation of the ability of the observer to predict experimental results, Richard Feynman called it a phenomenon which is impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery of quantum mechanics. 8 Overview If light consisted strictly of ordinary or classical particles, and these particles were fired in a straight line through a slit and allowed to strike a screen on the other side, we would expect to see a pattern corresponding to the size and shape of the slit. However, when this single-slit experiment is actually performed, the pattern on the screen is a diffraction pattern in which the light is spread out. The smaller the slit, the greater the angle of spread. The top portion of the image shows the central portion of the pattern formed when a red laser illuminates a slit and, if one looks carefully, two faint side bands. More bands can be seen with a more highly refined apparatus. Same double-slit assembly, 0.7 mm between slits, in top diffraction explains the pattern as being the result of the interference of light waves from the slit. Image: one slit is closed, In the single-slit image, a diffraction pattern, the faint spots on either side of the main band, forms due to the non-zero width of the slit. This diffraction pattern is also seen in the double-slit image, but if one illuminates two parallel slits, the light with many smaller interference fringes from the two slits again interferes. Here the interference is a more pronounced pattern with a series of alternating light and dark bands. The width of the bands is a property of the frequency of the illuminating light. 19. See the bottom photograph to the right. When Thomas Young, 1773–1829, first demonstrated this phenomenon, it indicated that light consists of waves, as the distribution of brightness can be explained by the alternately additive and subtractive interference of wave fronts. 8. Young's experiment, performed in the early 1800s, played a crucial role in the understanding of the wave theory of light, vanquishing the corpuscular theory of light proposed by Isaac Newton, which had been the accepted model of light propagation in the 17th and 18th centuries. Young's drawing of diffraction, however, the later discovery of the photoelectric effect, demonstrated that under different circumstances, light can behave as if it is composed of discrete particles. These seemingly contradictory discoveries made it necessary to go beyond classical physics and take into account the quantum nature of light. Feynman was fond of saying that all of quantum mechanics can be gleaned from carefully thinking through the implications of this single experiment. 20. He also proposed, as a thought experiment, that if detectors were placed before each slit, the interference pattern would disappear. 21. The Englert-Greenberger duality relation provides a detailed treatment of the mathematics of double-slit interference in the context of quantum mechanics. A low-intensity double-slit experiment was first performed by G. I. Taylor in 1909-22 by reducing the level of incident light until photon emission/absorption events were mostly non-overlapping. A slit interference experiment was not performed with anything other than light until 1961, when Klaus Johnson of the University of Tübingen performed it with coherent electron beams and multiple slits. 23-24. In 1974, the Italian physicists Pier Giorgio Merli, Gianfranco Misiroli, and Giulio Pazzi performed a related experiment using single electrons from a coherent source in a biprism beam splitter, showing the statistical nature of the buildup of the interference pattern, as predicted by quantum theory. 25-26. In 2002, the single electron version of the experiment was voted the most beautiful experiment by readers of Physics World. 27. Since that time a number of related experiments have been published, with a little controversy. 28. In 2012, Stefano Frabani and co-workers sent single electrons onto nano-fabricated slits, about 100 nm wide, and, by detecting the transmitted electrons with a single electron detector, they could show the buildup of a double-slit interference pattern. 29. Many related experiments involving the coherent interference have been performed. They are the basis of modern electron diffraction, microscopy, and high-resolution imaging. 30-31. In 2018, single particle interference was demonstrated for antimatter in the positron laboratory. https://www.positron.physi.polyme.it/right L.Nes, Politecnico di Milano, of Raffaele Farragut in Como, Italy, by a group led by Marco Giamarca. 32 variations of the experiment interference from individual particles. An important version of this experiment involves single particle detection. Sending coherent particles through a double-slit apparatus one at a time results in single particles being detected as white dots on the screen, as expected. Remarkably, however, an interference pattern emerges when these particles are allowed to build up one by one. See the image below. Experimental electron double-slit diffraction pattern. 33. Across the middle of the image at the top the intensity alternates from high to low, showing interference in the signal from the two slits. Bottom, movie of the pattern buildup dot by dot. Click on the thumbnail to enlarge the movie. This demonstrates the wave-particle duality, which states that all matter exhibits both wave and particle properties. The particle is measured as a single pulse at a single position, while the modulus squared of the wave describes the probability of detecting the particle at a specific place on the screen, giving a statistical interference pattern. 34. This phenomenon has been shown to occur with photons, 35 electrons, 36 atoms, and even some molecules, with Buckminster fullerene, C60, in 2001. 37, 38, 39, 40 with 2 molecules of 430 atoms, C60, C12F25, 10 and C168H94F15208N4S4, in 2011 41, and with molecules of up to 2,000 atoms in 2019 42 Mach-Zehnder interferometer. The Mach-Zehnder interferometer can be seen as a simplified version of the double-slit experiment. Instead of propagating through free space after the 2 slits, and hitting any position in an extended screen, in the interferometer the photons can only propagate via 2 paths, and hit 2 discrete photodetectors. This makes it possible to describe it via simple linear algebra in dimension 2, rather than differential equations. A photon emitted by the laser hits the first beam splitter and is then in a superposition between the 2 possible paths. In the second beam splitter these paths interfere, causing the photon to hit the photodetector on the right with probability 1, and the photodetector on the bottom. Photons in a Mach-Zehnder interferometer exhibit wave-like interference and particle-like detection at single photon detectors, with probability 0. It is interesting to consider what would happen if the photon were definitely in either of paths between the beam splitters. This can be accomplished by blocking one of the paths, or equivalently by detecting the presence of a photon there. In both cases there will be no interference between the paths anymore, and both photodetectors will be hit with probability 1/2. From this we can conclude that the photon does not take one path or another after the first beam splitter, but rather that it is in a genuine quantum superposition of the 2 paths. 43 Which-way experiments and the principle of complementarity. A well-known thought experiment predicts that if particle detectors are positioned at the slits, showing through which slit a photon goes, the interference pattern will disappear. 8 This which-way experiment illustrates the complementarity principle. That photons can behave as either particles or waves, but cannot be observed as both at the same time. 44, 45, 46 Despite the importance of this thought experiment in the history of quantum mechanics, for example, see the discussion on Einstein's version of this experiment, technically feasible realizations of this experiment were not proposed until the 1970s. 47 Naive implementations of the textbook thought experiment are not possible because photons cannot be detected without absorbing the photon. Currently, multiple experiments have been performed illustrating various aspects of complementarity. 48 An experiment performed in 1987-49-50 produced results that demonstrated that partial information could be obtained regarding which path a particle had taken without destroying the interference altogether. This wave-particle trade-off takes form of an inequality relating the visibility of the interference pattern and the distinguishability of the which-way paths. 51 Delayed choice and quantum eraser variations. Wheeler's delayed choice experiments demonstrate that extracting which path information after a particle passes through the slits can seem to retroactively alter its previous behavior at the slits. Quantum eraser experiments demonstrate that wave behavior can be restored by erasing or otherwise making permanently unavailable the which path information. A simple do-it-at-home illustration of the quantum eraser phenomenon was given in an article in Scientific American 52. If one sets polarizers before each slit with their axes orthogonal to a diagram of Wheeler's delayed each other, the interference pattern will be eliminated. The choice experiment, showing the polarizers, can be considered as introducing which path information principle of determining the path of to each beam. Introducing a third polarizer in front of the detector, the photon after it passes through with an axis of 45 degrees relative to the other polarizers erases the slit information, allowing the interference pattern to reappear. This can also be accounted for by considering the light to be a classical wave. 5291 and also when using circular polarizers and single photons. 53 6 Implementations of the polarizers using entangled photon pairs have no classical explanation. 53 Weak measurement. In a highly publicized experiment in 2012, researchers claimed to have identified the path each particle had taken without any adverse effects at all on the interference pattern generated by the particles. 54 In order to do this, they used a setup such that particles coming to the screen were not from a point-like source, but from a source with 2 intensity maxima. However, commentators such as Svensson 55 have pointed out that there is in fact no conflict between the weak measurements performed in this variant of the double-slit experiment and the Heisenberg uncertainty principle. Weak measurement followed by post-selection did not allow simultaneous position and momentum measurements for each individual particle, but rather allowed measurement of the average trajectory of the particles that arrived at different positions. In other words, the experimenters were creating a statistical map of the full trajectory landscape. 55 other variations. In 1967, Fleeger and Mondell demonstrated two-source interference using two separate lasers as light sources. 56-57 It was shown experimentally in 1972 that in a double-slit system where only one slit was open at any time, interference was nonetheless observed provided the path difference was such that the detected photon could have come from either slit. 58-59 The experimental conditions were such that the photon density in the system was much less than unity. In 1991, Carnell and Linek performed the classic Young's double-slit experiment with metastable helium atoms passing through micrometer-scale slits in gold foil. 60-61 In 1999, a quantum interference experiment, using a diffraction grating, rather than two slits, was successfully performed with buckyball molecules, each of which comprises 60 carbon atoms. 3762 A buckyball is large enough, diameter about 0.7 nm, nearly 500,000 times larger than a proton, to be seen in an electron microscope. In 2002, an electron field emission source was used to demonstrate the double-slit experiment. In this experiment, a coherent electron wave was a laboratory double-slit assembly, distance between emitted from two closely located emission sites on the needle apex, top posts is approximately which acted as double slits, splitting the wave into two coherent electron 2.5 cm, 1 inch waves in a vacuum. The interference pattern between the two electron waves could then be observed. 63 In 2017, researchers performed the double-slit experiment using light-induced field electron emitters. With this technique, emission sites can be optically selected on a scale of 10 nanometers. By selectively deactivating, closing, one of the two emissions slits, researchers were able to show that the interference pattern disappeared. 64 In 2005, Aloud presented an experimental and theoretical study of the optical transmission of a thin metal screen perforated by two sub-wavelength slits, separated by many optical wavelengths. The total intensity of the far-field double-slit pattern is shown to be near-field intensity distribution patterns for plasmonic slits with equal widths, A, and non-equal widths, B. Reduced or enhanced as a function of the wavelength of the incident light beam. 65 In 2012, researchers at the University of Nebraska-Lincoln performed the double-slit experiment with electrons as described by Richard Feynman, using new instruments that allowed control of the transmission of the two slits and the monitoring of single electron detection events. Electrons were fired by an electron gun and passed through one or two slits of 62 nm wide times 4 m tall. 66 In 2013, a quantum interference experiment, using diffraction gratings, rather than two slits, was successfully performed with molecules that each comprised 810 atoms, whose total mass was over 10,000 atomic mass units. 34 The record was raised to 2,000 atoms, 25,000 AMU. In 2019, 18 hydrodynamic pilot wave analogues. Hydrodynamic analogues have been developed that can recreate various aspects of quantum mechanical systems, including single particle interference through a double-slit. 67 A silicone oil droplet, bouncing along the surface of a liquid, self-propels via resonant interactions with its own wave field. The droplet gently sloshes the liquid with every bounce. At the same time, ripples from past bounces affect its course. The droplet's interaction with its own ripples, which form what is known as a pilot wave, causes it to exhibit behaviors previously thought to be peculiar to elementary particles, including behaviors customarily taken as evidence that elementary particles are spread through space like waves, without any specific location, until they are measured. 68-69 Behaviors mimicked via this hydrodynamic pilot wave system include quantum single particle diffraction, 70 tunneling, quantized orbits, orbital level splitting, spin, and multimodal statistics. It is also possible to infer uncertainty relations and exclusion principles. Videos are available illustrating various features of this system. See the external links. However, More complicated systems that involve two or more particles in superposition are not amenable to such a simple, classically intuitive explanation. 71 Accordingly, no hydrodynamic analog of entanglement has been developed. 67 Nevertheless, optical analogs are possible. 72 Double-slit experiment on time. In 2023, an experiment was reported recreating an interference pattern in time by shining a pump laser pulse at a screen coated in indium tin oxide, ITO, which would alter the properties of the electrons within the material due to the Kerr effect, changing it from transparent to reflective for around 200 femtoseconds long, where a subsequent probe laser beam hitting the ITO screen would then see this temporary change in optical properties as a slit in time, and two of them as a double slit with a phase difference adding up destructively or constructively on each frequency component, resulting in an interference pattern. 73 74 75 Similar results have been obtained classically on water waves. 73-75 Classical wave optics formulation. Much of the behavior of light can be modeled using classical wave theory. The Huygens-Fresnel principle is one such model. It states that each point on a wave front generates a secondary wavelet, and that the disturbance at any subsequent point can be found by summing the contributions of the individual wavelets at that point. This summation needs to take into account the phase as well as the amplitude of the individual wavelets. Only the intensity of a light field can be measured. This is proportional to the square of the amplitude. In the double-slit experiment, the two slits are illuminated by the quasi-monochromatic light of a single laser. If the width of the slits is small enough, much less than the wavelength of the laser light, the slits diffract the light into cylindrical waves. These two cylindrical wave fronts are superimposed, and the amplitude, and therefore the intensity, at any point in the combined wave fronts depends on both the magnitude and the phase of the two wave fronts. The difference in phase between the two waves is determined by the difference in the distance traveled by the two waves. If the viewing distance is large compared with the separation of the slits, the far field, the phase difference can be found using the geometry shown in the figure below right. The path difference between two waves traveling at an angle is given by two-slit diffraction pattern with an incident of plane wave, where d is the distance between the two slits. When the two waves are in phase, i.e. the path difference is equal to an integral number of wavelengths, the summed amplitude, and therefore the summed intensity is maximum, and when they are in anti-phase, i.e. the path photo of the double-slit interference of sunlight, difference is equal to half a wavelength, 1.5 wavelengths, etc., then the two waves cancel and the summed intensity is zero. This effect is known as interference. The interference fringe maxima occur at angles where is the wavelength of the light. The angular spacing of the fringes, f, is given by the spacing of the fringes at a distance z from the slits is given by two slits are illuminated by a plane wave, showing the path difference. For example, if two slits are separated by 0.5 mm, d, and are illuminated with a 0.6 m wavelength laser, then at a distance of 1 m, z, the spacing of the fringes will be 1.2 mm. If the width of the slits b is appreciable compared to the wavelength, the Fraunhofer diffraction equation is needed to determine the intensity of the diffracted light as follows. 76 Where the sin function is defined as sin x equals sin x / x for x0, and sin 0 equals 1. This is illustrated in the figure above, where the first pattern is the diffraction pattern of a single slit, given by the sin function in this equation, and the second figure shows the combined intensity of the light diffracted from the two slits, where the cos function represents the fine structure, and the coarser structure represents diffraction by the individual slits as described by the sin function. Similar calculations for the near field can be made by applying the Fresnel diffraction equation, which implies that as the plane of observation gets closer to the plane in which the slits are located, the diffraction patterns associated with each slit decrease in size, so that the area in which interference occurs is reduced, and may vanish altogether when there is no overlap in the two diffracted patterns. 77 Path integral formulation. The double-slit experiment can illustrate the path integral formulation of quantum mechanics provided by Feynman. 78 The path integral formulation replaces the classical notion of a single, unique trajectory for a system, with the sum over all possible trajectories. The trajectories are added together by using functional integration. Each path is considered equally likely, and thus contributes the same amount. However, the phase of this contribution at any given point along the path is determined by the action along the path. All these contributions are then added together, and the magnitude of the final result is squared, to get the probability distribution for the position of a particle. As is always the case when calculating probability, the results must then be normalized by imposing one of an infinite number of equally likely paths used in the Feynman path integral. See also, Wiener process. The probability distribution of the outcome is the normalized square of the norm of the superposition, over all paths from the point of origin to the final point, of waves propagating proportionally to the action along each path. The differences in the cumulative action along the different paths, and thus the relative phases of the contributions, produces the interference pattern observed by the double-slit experiment. Feynman stressed that his formulation is merely a mathematical description, not an attempt to describe a real process that we can measure. Interpretations of the experiment like the Schrödinger's cat thought experiment, the double-slit experiment is often used to highlight the differences and similarities between the various interpretations of quantum mechanics. Copenhagen interpretation. The Copenhagen interpretation is a collection of views about the meaning of quantum mechanics, stemming from the work of Niels Bohr, Werner Heisenberg, Max Born, and others. The term Copenhagen interpretation was apparently coined by Heisenberg during the 1950s to refer to ideas developed in the 1925 to 1927 period, glossing over his disagreements with Bohr 79, 80, 81, 82. Consequently, there is no definitive historical statement of what the interpretation entails. Features common across versions of the Copenhagen interpretation include the idea that quantum mechanics is intrinsically indeterministic, with probabilities calculated using the Born rule, and the principle of complementarity, which states that objects have certain pairs of complementary properties that cannot all be observed or measured simultaneously. 83. Moreover, the act of observing or measuring an object is irreversible, and no truth can be attributed to an object, except according to the results of its measurement. A particular experiment can demonstrate particle behavior, passing through a definite slit, or wave behavior, interference, but not both at the same time. 84, 85, 167, 86. Copenhagen type interpretations hold that quantum descriptions are objective, in that they are independent of physicists' personal beliefs and other arbitrary mental factors. 85, 85-90. The results from the most basic double-slit experiment, the observation of an interference pattern, is explained by wave interference from the two paths to the screen from each of the two slits. 8. The single particle results show that the waves are probability amplitudes which square to produce a probability distribution. 8. The particles are discrete and identical. Many are needed to build up the full interference pattern. 8. The results from some of the which-way experiments are described as observations of complementarity. 87. Modifying the experiment to monitor the slit suppresses the interference pattern. 88. 155. Other which-way experiments make no mention of complementarity in their analysis. 89. Relational interpretation. According to the relational interpretation of quantum mechanics, first proposed by Carlo Rovelli, 90 observations such as those in the double-slit experiment result specifically from the interaction between the observer, measuring device, and the object being observed, physically interacted with, not any absolute property possessed by the object. In the case of an electron, if it is initially observed at a particular slit, then the observer-particle, photon-electron, interaction includes information about the electron's position. This partially constrains the particle's eventual location at the screen. If it is observed, measured with a photon, not at a particular slit but rather at the screen, then there is no which path information as part of the interaction, so the electron's observed position on the screen is determined strictly by its probability function. This makes the resulting pattern on the screen the same as if each individual electron had passed through both slits. Many worlds interpretation. As with Copenhagen, there are multiple variants of the many worlds interpretation. The unifying theme is that physical reality is identified with a wave function, and this wave function always evolves unitarily, i.e., following the Schrödinger equation with no collapses. 91-92. Consequently, there are many parallel universes, which only interact with each other only through interference. David Deutsch argues that the way to understand the double-slit experiment is that in each universe the particle travels through a specific slit, but its motion is affected by the interference with particles in other universes. This creates the observable fringes. 93 David Wallace, another advocate of the many worlds interpretation, writes that in the familiar setup of the double-slit experiment the two paths are not sufficiently separated for a description in terms of parallel universes to make sense. 94 De Broglie-Bohm theory. An alternative to the standard understanding of quantum mechanics, the de Broglie-Bohm theory states that particles also have precise locations at all times, and that their velocities are defined by the wave function. So while a single particle will travel through one particular slit in the double-slit experiment, the so-called pilot wave that influences it will travel through both. The two-slit de Broglie-Bohm trajectories were first calculated by Chris Dewdney while working with Chris Philippides and Basil Hilly at Birkbeck College, London. 95 The de Broglie-Bohm theory produces the same statistical results as standard quantum mechanics, but dispenses with many of its conceptual difficulties by adding complexity through an ad hoc quantum potential to guide the particles. 96 While the model is in many ways similar to Schrödinger equation, it is known to fail for relativistic cases. 97 And does not account for features such as particle creation or annihilation in quantum field theory. Many authors such as Nobel laureates Werner Heisenberg 98, Sir Anthony James Leggett 99 and Sir Roger Penrose 100 have criticized it for not adding anything new. More complex variants of this type of approach have appeared, for instance the three-wave hypothesis 101-102 of Rizard-Hradecki, as well as other complicated combinations of de Broglie and Compton waves 103, 104, 105. To date there is no evidence that these are useful. Bohmian trajectories of particles in de Broglie-Bohm theory in the double-slit experiment. 100 trajectories guided by the wave function. In de Broglie-Bohm's theory, a particle is represented, at any time, by a wave function in a position, center of mass. This is a kind of augmented reality compared to the standard interpretation. Numerical simulation of the double-slit experiment with electrons. Figure on the left, evolution, from left to right, of the intensity of the electron beam at the exit of the slits, left, up to the detection screen located 10 cm after the slits, right. The higher the intensity, the more the color is light blue. Figure in the center, impacts of the electrons observed on the screen. Figure on the right, intensity of the electrons in the far field approximation, on the screen. Numerical data from Klaus Johnson's experiment, 1961. Photons, atoms, and molecules follow a similar evolution. See also Aharonov-Bohm effect, complementarity, physics, delayed choice, quantum eraser, diffraction from slits, dual polarization, interferometry, Elitzur-Vaidman-Bohm tester, N-slit interferometer, matter wave photon polarization, quantum coherence, Schrödinger's cat, Young's interference experiment, measurement problem, hydrodynamic quantum analogues, pilot wave theory. References 1. Young, Thomas, 1804. The Bake-Ryan Lecture. Experiments and Calculation Relative to Physical Optics. https://doi.org/10.1098% 2 FRSTL.1804.0001. Philosophical Transactions of the Royal Society of London. 94, 1-16. doi 10.1098/RSTL.1804.0001, https://doi.org/10.1098% 2 FRSTL.1804.0001. S2CID 11040839, https://api.semanticscholar.org/corpus ID 11040839. 2 Thompson, G.P., Reed, A. 1927. Diffraction of cathode rays by a thin film, https://www.anatur.com/articles/119890 right parenthesis. Nature. 119, 3007 890. Bibcode 1927 Natur.119 Q.890 T. https://ui.adsabs.harvard.edu/abs/1927natur.119q.890t doi 10.1038/1198990 https://doi.org/10.1038% 2f1198990 ISSN 0028-0836 https://www.worldcat.org/isn/0028-0836 S2CID 412-2313 https://api.semanticscholar.org/corpus ID 4122313 3 Physicists smash record for wave-particle duality https://medium.com/thephysicsarchive blog/462C39db8E7b 4 Ebenberger, Sandra, ETAL 2013 Matter-wave interference with particles selected from a molecular library with masses exceeding 10,000 AMU. Physical Chemistry Chemical Physics 15, 35 14696 to 14700 AR 14 13 10.83 43 https://arxiv.org/abs/13 10.83 43 Bibcode 2013 PCCP 15146996E https://ui.adsabs.harvard.edu/abs/2013 PCCP 15146996E doi 10.1039/C3CP51500A https://doi.org/10.1039% 2FC3CP51500A PMID 239007110 https://pubmed.inspi.nlm.nih.gov/239007110 S2CID 394-4699 https://api.semanticscholar.org/corpus ID 3944699 5 While there is no doubt that Young's demonstration of optical interference, using sunlight, pinholes, and cards, played a vital part in the acceptance of the wave theory of light, there is some question as to whether he ever actually performed a double-slit interference experiment. Robinson, Andrew, 2006. The Last Man Who Knew Everything, https://archive.org/details/lastmanwhenuf00 roby/page/123. New York, New York, Pi Press. Pages 123 to 124, https://archive.org/details/lastmanwhoknew 00 roby/page/123 right parenthesis. ISBN 978-0-13-133430-7. 6 Kipnis, Nam S. 1991. History of the Principle of Interference of Light, https://books.google.com/books, ID equals E7FVAAAAMAAJ. Springer. P65. ISBN 9780817623166. 7 Laterman, Leon M., Christopher T. Hill, 2011. Quantum Physics for Poets, https://books.google.com/books?ID=QY_YOHG_WYC and PG=PA102. U.S. Prometheus Books. Pages 102 to 111. ISBN 978-1616142810. 8 Feynman, Richard P., Robert B. Leighton, Matthew Sands, 1965. The Feynman Lectures on Physics, Volume 3. Addison Wesley. Pages 1.1 to 1.8. ISBN 978-0201021189. 9 Feynman, 1965, p. 1.510. Darling, David, 2007. Wave-particle duality, http://www.daviddarling.info/encyclopedia-wave-particle_duality.html. The Internet Encyclopedia of Science. The Worlds of David Darling. Retrieved October 18, 2008. 11 Feynman, 1965, p. 1.712. Leon Lederman, Christopher T. Hill, September 27, 2011. Quantum Physics for Poets, https://books.google.com/books, ID equals QI_YOHG_WIC and PG equals PA 109. Prometheus Books, Publishers. P 109. ISBN 978-1-61614-281-0. 13. If in a double-slit experiment, the detectors which register outcoming photons are placed immediately behind the diaphragm with two slits, a photon is registered in one detector, not in both. Muller-Kirsten, H.J.W., 2006. Introduction to Quantum Mechanics, Schrödinger Equation and Path Integral, https://books.google.com/books, ID equals P1_Z81LE58MC and PG equals PA14. U.S. World Scientific. P14. ISBN 978-981-2566911. 14 Plotnitsky, Arkady, 2012. Niels Bohr and Complementarity, An Introduction, https://books.google.com/books ? ID =DMD up 97S4IC and PG equals PA 75. U.S. Springer. Pages 75 to 76. ISBN 9781461445173. 15. It seems that light passes through one slit or the other in the form of photons if we set up an experiment to detect which slit the photon passes, but passes through both slits in the form of a wave if we perform an interference experiment. Ray, Alistair I.M., 2004. Quantum Physics, Illusion or Reality. https://books.google.com/books, ID equals FTGUC6G4C and PG equals PA9. UK, Cambridge University Press. Pages 9 to 10. ISBN 978-1139455275. 16 Feynman, The Feynman Lectures on Physics, 3 Quantum Mechanics p.1-1. There is one lucky break, however electrons behave just like light. 17 C. Davison Germer Experiment Davison, C.J., 1928. The Diffraction of Electrons by a Crystal of Nickel. Bell System Technical Journal. 7, 90-105. doi 10.1002/J.15387305.1928.TB00342.X, https://doi.org/10.1002%2FJ.1538-7305.1928.TB00342.X. 18 Yakov Wyfien, Philip Geyer, Patrick Zwick, Philip Kiaka, Sebastian Pedalino, Marcel Mayer, Stefan Gerlich, Marcus Arndt, September 2019. Quantum Superposition of Molecules Beyond 25 Keta. Nature Physics. 15, 12-1242-1245. Bibcode 2019 NAT PH 15.1242F. https://ui.adsabs.harvard.edu/abs/2019 NAT PH 15.1242F. doi 10.1038/S41567-019-0663-9, https://doi.org/10.1038%2FS41567-019-0663-9. S2CID20363828, https://api.semanticscholar.org/corpus ID 20363828. 19 Charles Sanders Peirce first proposed the use of this effect as an artifact-independent reference standard for length. C.S. Peirce, July 1879. Note on the progress of experiments for comparing a wavelength with a meter. American Journal of Science, as referenced by Crease, Robert P., 2011. World in the Balance, The Historic Quest for an Absolute System of Measurement. New York, W. W. Norton. p. 317. ISBN 978-0-393-07298-3. p. 203. 20 Green, Brian, 1999. The Elegant Universe, Superstrings, Hidden Dimensions, and the Quest for the Ultimate Theory. https://archive.org/details/elegantuniverses0000gre/page/97. New York, W. W. Norton. Pages 97 to 109. https://archive.org/details/elegantuniverses0000gre/page/97. ISBN 978-0-393-04688-5. 21 Feynman, 1965, Chapter 322. Sir Geoffrey, Ingram Taylor, 1909. Interference Fringes with Feeble Light. Professor Cam. Philosophy SOC 15, 114. 23 Johnson, Klaus, August 1, 1961. Elektroninterferenzen in mehreren Kunstliche Gestalten Feinspalten. Zeitschrift für Physik, in German. 161, 454-474. Bibcode 1961 ZPHY 161 454J. https://ui.adsabs.harvard.edu/abs/1961 ZPHY 161 454J. doi 10.1007/bf01342460. https://doi.org/10.1007% 2FBF01342460. ISSN 0044-3328. https://www.worldcat.org/isn/00443328. S2CID 1216599705. https://api.semanticscholar.org/crpsid 1216599705. 24 Johnson, Klaus, January 1, 1974. Electron diffraction at multiple slits. American Journal of Physics. 42, 1-4-11. Bibcode 1974 MJ42, 4J. https://ui.adsabs.harvard.edu/abs/1974 MJ42, 4J. doi 10.1119/1.1987592. https://doi.org/10.1119% 2F1.1987592. ISSN 0002-9505. https://www.worldcat.org/isn/0002-9505. 25 Merli, P.G., Misirli, G.F., Pazzi, G., 1976. On the Statistical Aspect of Electron Interference Phenomena. American Journal of Physics. 44, 306-307. Bibcode 1976 MJ44306M. https://ui.adsabs.harvard.edu/abs/1976 MJ44306M. doi 10.1119/1.10184. https://doi.org/10.1119% 2F1.10184. 26 Rosa, R., 2012. The Merli-Misirli Pazzi two-slit electron interference experiment, https://www.inspi.nlm.nih.gov/pmc/articles/pmc4617474. Physics in Perspective. 14. 2178-194. Bibcode 2012 PHP 14178R. https://ui.adsabs.harvard.edu/abs/2012 PHP 14178R. doi 10.1007/S00016-011-0079-0. https://doi.org/10.1007%2fs0016011-00079-0. PMC 461-7474. https://www.inspi.nlm.nih.gov/pmc/articles/pmc 4617474. PMID 265255832. https://pubmed.inspi.nlm.nih.gov/265255832. 27. The Most Beautiful Experiment. https://physicsworld.com/a/the double-slit experiment/ Physics World 2002 archived. https://web.archive.org/web/20210524080643/https://physicsworld.com/the-double-slit-experiment/right May 24, 2021 at the Wayback Machine 28. Steeds, John, Merle, Pier Giorgio, Pazzi, Giulio, Misiroli, Gianfranco, Tonomura, Akira, 2003. The Double-Slit Experiment with Single Electrons. https://ioscience.iop.org/article/1088/2058/16/5/24. Physics World. 16. 520-21 doi 10.1088/2058-7058/16/5/24. https://doi.org/10.1088%2f2058-7058%2f16%2f5%2f24. ISSN 0953-8585. https://www.worldcat.org/ISSN/0953-8585 right parenthesis. 29 Frabani, Stefano, Gabriele, Alessandro, Carlo Gazzetti, Gian, Giorgi, Filippo, Matucci, Giorgio, Pazzi, Giulio, Cesari, Nicola Semprini, Villa, Moro, Zaccoli, Antonio, May 2012. The Young-Feynman two-slits experiment with single electrons. Build-up of the interference pattern in arrival time distribution using a fast readout pixel detector. Ultramicroscopy. 116, 73-76. doi 10.1016/j.ultramic.2012.03.017. https://doi.org/10.1016%2fj.ultramic.2012.03.017. ISSN 0304-3991. https://www.worldcat.org/isn/0304-3991. 30 Cowley, J.M., 1995. Diffraction Physics. North Holland Personal Library, 3rd ed. Amsterdam, Elsevier. ISBN 978-0-444-82218-5. 31 Spence, John C. H., 2017. High-Resolution Electron Microscopy, 4th edition, first published in paperback ed. Oxford, Oxford University Press. ISBN 978-0-19-879583-4. 32 Sala, S., Arigia, A., Erudito, A., Farragut, R., Guyamarchi, M., Leon, M., Pistolo, C. Scampoli, p. 2019. First demonstration of antimatter wave interferometry. https://www.ncbi.nlm.nih.gov/pmc/articles/pmc64995993 right parenthesis. Science Advances 5 EAAV7610 Bibcode 2019 SciA 5.7610s https://ui.adsabs.harvard.edu/abs/2019 SciA 5.7610s doi 10.1126/sciadv.off7610 https://doi.org/10.1126% tufciadv.off7610 PMC 649-9593 https://www.inspi.nlm.nih.gov/pmc/articles/pmc 6499593 PMID 310582223 https://pubmed.ncbi.nlm.nih.gov/310582223 right parenthesis 33 Bach, Roger, Pope, Damien, Liu, S.Y. Wang, Beit Lon, Herman, March 13, 2013. Controlled double-slit electron diffraction, https://ioscience.iop.org/article/10.1088/1367-2630/15/3/033018. New Journal of Physics. IOP Publishing. 15. 3033018 AR141210.6243, https://arxiv.org/abs/1210.6243. Bibcode 2013 NJPH. 15C3018B, https://ui.adsabs.harvard.edu/abs/2013 NJPH. 15C3018B. doi 10.1088/1367-2630/15/3/033018 https://doi.org/10.1088% 2f1367-2630% 2f15% 2f3% 2f0333018 ISSN 1367-2630 https://www.worldcat.org/isn/1367-2630 S2CID 832961 https://api.semanticscholar.org/corpus ID 832961 34 Green, Brian, 2007. The Fabric of the Cosmos, Space, Time, and the Texture of Reality, https://books.google.com/books, ID equals DND2K6 MXELPIC and PG equals PA90. Random House LLC. P90. ISBN 978-0-307-42853-0. 35 Ananthaswamy, Anil, 2018. Through Two Doors at Once, the elegant experiment that captures the enigma of our quantum reality. Penguin. P63. ISBN 978-1101986110. 36 Donati, O, Miserly, G.F., Pazzi, G. 1973. An Experiment on Electron Interference. American Journal of Physics. 41, 5639-644. Bibcode 1973 MJ41639D, https://ui.adsabs.harvard.edu/abs/1973 MJ41639D. doi 10.1119/1.1987321, https://doi.org/10.1119% 2f1.1987321. 37 New Scientist, Quantum Wonders, Corpuscles and Buckyballs, 2010, https://www.newscientist.com/article/mg20627596.100 Quantum Wonders Corpuscles and Buckyballs.html. Introduction. Subscription needed for full text. Quoted in full in 1. http://postbiota.org/pipermal/tt/2010 may/0073336.html. Archived. https://web.archive.org/postbiota.org/pipermail/tt/2010-may/0073336.html. Right parenthesis September 25, 2017 at the Wayback Machine. 38. Wave particle duality of C60. http://www.quantum.at/research/molecule-interferometry-foundation/wave particle duality of C60.html. Archived. https://web.archive.org/web/201033115055/http:/www.quantum.at/research/molecule-interferometry-foundation/wave particle duality of C60.html. March 31, 2012 at the Wayback Machine. 39. Nertz, Olaf, Bresger, Bjorn, Arndt, Marcus, Zielinger, Anton. 2001. Diffraction of complex molecules by structures made of light. Physical Reverend Let. 87. 16160401 AR14 Quanf/01100012. https://arxiv.org/abs/quantph/01100012. Bibcode 2001 PHRVL 87P0401N. https://ui.adsabs.harvard.edu/abs/2001 PHRVL 87P0401N. doi 10.1103/FISREVLET.87.1604001. https://doi.org/10.1103% FISREVLET.87.1604001. PMID 11690188. https://pubmed.inspy.nlm.nih.gov/11690188 right parenthesis. S2CID 215473661. https://api.semanticscholar.org/corpus ID 215473661. 40 Nertz, O, Arndt, M, Zielinger, A. 2003. Quantum interference experiments with large molecules. https://web.archive.org/20150604203129/http://vcq.quantum.at/fileadmin/p/application/2003-17.pdf. PDF. American Journal of Physics. 71. 4319-325. Bibcode 2003 MJF 71319N. https://ui.adsabs.harvard.edu/abs/2003 MJF 71319N. doi 10.1119/1.153158. https://doi.org/10.1119% 2f1.15315880. Archived from the original. https://vcq.quantum.at/fileadmin/publications/2003-17.pdf. PDF. On June 4, 2015. Retrieved June 4, 2015. 41 Stefan Gerlich, ETAL, April 5, 2011. Quantum interference of large organic molecules. https://www.inspy.nlm.nih.gov/pmc/articles/pmc3104521. Nature Communications. 2, 263. Bibcode 2011 Netco, 2263G, https://ui.adsabs.harvard.edu/abs/2011 Netco, 2263G. DOI 10.1038/NCMS1263, https://doi.org/10.1038%2/NCMS1263. PMC 310-4521, https://www.ncbi.nlm.nih.gov/pmc/articles/PMC 310-4521 right parenthesis. PMID 214680015, https://pubmed.nspi.nlm.nih.gov/214680015 right parenthesis. 42 Yakov Fien, ETAL, December 2019. Quantum superposition of molecules beyond 25 kDa, https://www.nature.com/articles/S4157-019-0663-9.ev. Nature Physics. 15, 12-12-42 1245. Bibcode 2019 Nat pH 15.1242F, https://ui.adsabs.harvard.edu/abs/2019 Nat pH 15.1242F. DOI 10.1038/S41567-019-0663-9, https://doi.org/10.1038%2FS41567-019-0663-9. S2CID 203638258, https://api.semanticscholar.org/corpus ID 203638258. 43 Vidral, Vilatko, 2006. Introduction to Quantum Information Science. Oxford University Press. ISBN 9780199215706. OCLC 4423514998, https://www.worldcat.org/iclc/4423514998. 44 Harrison, David, 2002. Complementarity in the Copenhagen Interpretation of Quantum Mechanics, http://www.upscale.utoronto.ca/general-interest/harrison/complementarity/compcopen.html. Upscale. Department of Physics, U of Toronto. Retrieved June 21, 2008. 45 Cassidy, David, 2008. Quantum Mechanics 1925-1927, Triumph of the Copenhagen Interpretation, https://web.archive.org/web/2016014094094044/https://www.ipe.org/history/Heisenberg/p09.htm. Werner Heisenberg. American Institute of Physics. Archived from the original, http://www.aip.org/history/Heisenberg/p09.htm right parenthesis on January 14, 2016. Retrieved June 21, 2008. 46 Bosca Diaz Pintado, Maria C., 29-31 March 2007. Updating the wave-particle duality, http://folskyarchive.pit.edu/archive/00003568/. 15th UK and European Meeting on the Foundations of Physics. Leeds, UK. Retrieved June 21, 2008. 47 Bartel, L., 1980. Complementarity in the double-slit experiment, on simple realizable systems for observing intermediate particle wave behavior. Physical Review D21, 6/1698-1699. Bibcode 1980 PHRVD. 21.1698b, https://ui.adsabs.harvard.edu/abs/1980 doi 10.1103/FSREV.21.1698 https://doi.org/10.1103% 2 FSREV.21.1698 48 Zeilinger, A. 1999. Experiment and the Foundations of Quantum Physics. Reviews of Modern Physics. 71, 2S288S297. Bibcode 1999 RVMPS. 71288Z, https://ui.adsabs.harvard.edu/abs/1999 RVMPS 71288Z. doi 10.1103/RevMod Physical.71.S288 https://doi.org/10.1103% 2 FrevMod Phys.71.S288 49 P. Mittelstat, A. Prieur, R. Schieder, 1987. Unsharp particle wave duality in a photon split beam experiment. Foundations of Physics. 17, 9891-903. Bibcode 1987 FOPH, 17891M, https://ui.adsabs.harvard.edu/abs/1987 FOPH, 17891M. doi 10.1007/BF00734319, https://doi.org/10.1007% 2 FBF00734319. S2CID 122856271, https://api.semanticscholar.org/corpus ID 122856271. 50 DM Greenberger and A. Yasin, Simultaneous Wave and Particle Knowledge in a Neutron Interferometer, Physics Letters A 128, 391-4, 1988. 51 Sen, D. 2014. The Uncertainty Relations in Quantum Mechanics, https://www.jaster.org/stablue/24103129. Current Science. 107, 203-218. ISSN 0011-3891, https://www.worldcat.org/isn/00113891. However, the wave-particle trade-off is now expressed in terms of an inequality, known as Englert-Greenberger duality or simply wave-particle duality relation. See also Ref 24 in this work. 52 Hilmer, R., Kwiat, P. 2007. A Do-It-Yourself Quantum Eraser, https://www.scientificamerica.com/slideshow/a-do-it-yourself-quantum-eraser/right Scientific American. Volume 296, Number 5. Pages 90-95. Bibcode 2007 Siam.296E90H, https://ui.adsabs.harvard.edu/abs/2007 Siam.296E90H. doi 10.1038/Scientific American 0507-90, https://doi.org/10.1038% 2 Scientific American 0507-90. Retrieved January 11, 2016. 53 Tiao, R.Y., P.G. Kwiat, Steinberg, A.M., 1995. Quantum Non-Locality in Two-Photon Experiments at Berkeley. Quantum and Semi-Classical Optics, Journal of the European Optical Society Part B7, 3259-278 AR14 Quant PH/9501016, https://arxiv.org/abs/quant PH/9501016. Bibcode 1995 QSOP, 7259C, https://ui.adsabs.harvard.edu/abs/1995 CHUSOP 7259C doi 10.1088/1355-5111/7/3/006 https://doi.org/10.1088% 2f1355-5111% 2f7% 2f3% 2f006 S2CID11898796 https://api.semanticscholar.org/corpus ID 11898796 54 Francis, Matthew, May 21, 2012. Disentangling the wave-particle duality in the double-slit experiment, https://arstechnica.com/science/2012/05/ disentangling the wave-particle duality y in the double-slit experiment / Ars Tech Nica. 55 Svensson, Benke Y. 2013. Pedagogical Review of Quantum Measurement Theory with an emphasis on weak measurements. Quanta. 2, 118-49 AR 14-1202.5148, https://arxiv.org/abs/1202.5148, doi 10.12743/quanta.v2i1.12, https://doi.org/10.12743% 2f-quanta.v2i112. S2CID1192425777, https://api.semanticscholar.org/corpus ID 1192425777. 56 Flieger, R.L., Mondel, L., July 1967. Interference of independent photon beams. Physical Review. 159, 5-1084-1088. Bibcode 1967 PHRV. 159.1084p, https://ui.adsabs.harvard.edu/abs/1967 PHRV 159.1084p. doi 10.1103/physicalrev.159.1084, https://doi.org/10.113% 2fsrev.159.1084. 57 Interference of independent photon beams, the Flieger-Mondel experiment, https://web-archive.org/web/2011/interference_of_independent_ph.php. Archived from the original. http://scienceblogs.com/principles/2010/11/interference_of_independent_ph.php, on January 3, 2011. Retrieved June 16, 2011. 58 Silito, R.M., Wykes, Catherine, 1972. An interference experiment with light beams modulated in antiphase by an electro-optic shutter. Physics Letters A39, 4333-334. Bibcode 1972 PHLA, 39333S, https://ui.adsabs.harvard.edu/abs/1972 PHLA, 39333S. doi 10.1016/0375-9601, 72, 91015-8, https://doi.org/10.1016% 2f0375-9601% 2872% 2991015-8. 59 To a light particle, http://www.silittopics.co.uk/80rms_35.html right parenthesis. 60 Carnell, O., Linek, J., May 1991. Young's double-slit experiment with atoms, a simple atom interferometer. Physical Review Letters. 66, 212689 to 2694. Bibcode 1991 PHRVL 66.2689C. https://ui.adsabs.harvard.edu/abs/1991 PHRVL 66.2689C. doi 10.1103/physicalrevlet.66.2689. https://doi.org/10.1103% 2fsrevlet.66.2689. PMID 100435591. https://pubmed.inspy.nlm.nih.gov/10043591. 61 Carnell, O. Linek, J. 1991. Young's double-slit experiment with atoms, a simple atom interferometer. https://journals.aps.org/prl/pdf/10.1103/physicalrevlet.66.2689. Physical Review Letters 66, 212689 to 2692. Bibcode 1991 PHRVL 66.2689C. https://ui.adsabs.harvard.edu/abs/1991 PHRVL 66.2689C. doi 10.1103/physicalrevlet.66.2689. https://doi.org/10.1103% 2fsrevlet.66.2689. PMID 100435591. https://pubmed.inspy.nlm.nih.gov/10043591. Retrieved March 20, 2022. 62 Arndt, Marcus, Nertz, Olaf, Voss Andrea, Julian, Keller, Claudia, van der Zuu, Gerbrand, Zielinger, Anton, 1999. Wave-particle duality of C60 molecules. Nature. 401, 6754 680 Bibcode 1999 Natur.401680a. https://ui.adsabs.harvard.edu/abs/1999 Natur.401680a. doi 10.1038/44348. https://doi.org/10.1038% 2f44348. PMID 1849417. https://pubmed.ncbi.nlm.nih.gov/1849417 right parenthesis. S2CID 442-4892. https://api.semanticscholar.org/corpus ID 442-4892. 63 Oshima, C. Mastuda, K. Kona, T. Megami, Y. Kamaki, M. Murata, Y. Yamashita, T. Kuzumaki, T. Horiuk, Y. January 4, 2002. Young's interference of electrons in field emission patterns. https://link.aps.org/doi/10.1103/physicalrevlet.88.038301. Physical Review Letters 88, 30380301. Bibcode 2002 PHRVL 88C83010. https://ui.adsabs.harvard.edu/abs/2002 PHRVL 88C83010. doi 10.1103/physicalrevlet.88.038301. https://doi.org/10.1113% 2fsrevlet.88.038301. ISSN 0031-9007. https://www.worldcat.org/isn/0031-9007. PMID 11801091. https://pubmed.inspi.nlm.nih.gov/11801091. 64 Yanagisawa, Hirofumi, Chapina, Marcello, Hafner, Christian, Scots, Johannes, Osterwalder, Jurg, Kling, Matthias F., October 4, 2017. Optical control of Young's type double-slit interferometer for laser-induced electron emission from a nanotip. https://www.ncbi.nlm.nih.gov/pmc/articles/pmc5627254 right parenthesis. Scientific reports. 7. 112661 AR141710.02216. https://arxiv.org/abs/1710.02216. Bibcode 2017 NAT-SR 712661Y. https://ui.adsabs.harvard.edu/abs/2017 NAT-SR 712661Y. doi 10.1038/S41598-017-12832-3. https://doi.org/10.1038%2FS41598-017-12832-3. ISSN 2045-2322. https://www.worldcat.org/SN/2045-2322. PMC562-7254. https://www.inspi.nlm.nih.gov/pmc/articles/pmc5627254. PMID 289789114. https://pubmed.inspi.nlm.nih.gov/289789114. 65 Schouten, H.F., Kuzmin, N., Dubois, G., Visser, T.D., Burr, G., Alkmaid, P.F.A., Bloch, H., Hooft, G.W., Lenstra, D., Ilile, E.R., February 7, 2005. Plasmin-assisted two-slit transmission, Young's experiment revisited. http://repos.2delft.nl/islander/subject/UUID%385F0A85@6408AC88F3202882C235CH/datastream/OBJ/view. Physical Reverend Let. 94. 50533901. Bibcode 2005 PHRVL. 94E3901S. https://ui.adsabs.harvard.edu/abs/2005 PHRVL 94E3901S. doi 10.1103/FSRevlet.94.053901. https://doi.org/10.1103%2FSRevlet.94.053901. HDL 1887/71482. https://hdl.handle.net/1887%2F71482. PMID 157836441. https://pubmed.ncbi.nlm.nih.gov/157836441 right parenthesis. S2CID 19197175. https://api.semanticscholar.org/corpus ID 19197175. 66 Bach, Roger, ETAL, March 2013. Controlled double-slit electron diffraction. New Journal of Physics. 15. 3033018 AR141210.6243. https://arxiv.org/abs/1210.6243. Bibcode 2013 NJPH. 15C3018B. https://ui.adsabs.harvard.edu/abs/2013 NJPH. 15C3018B. doi 10.1088/1367-2630/15/3/0333018 https://doi.org/10.1088%2f1360/2630%2f3%2f0333018 S2CID 832961 https://api.semanticscholar.org/corpus ID 832961 67 Bush, John W. M. 2015. Pilot Wave Hydrodynamics. http://math.mit.edu/tilde-bush/wordpress/wp-content/upload/2015/0/bush/nrev2015.pdf, PDF. Annual Review of Fluid Mechanics. 47, 1-269-292. Bibcode 2015 and RFM 47269B, https://ui.adsabs.harvard.edu/abs/2015 and RFM 47269B. doi 10.1146/Anurev Fluid 010814-014506, https://doi.org/10.1146%2 Fanurev Fluid 010814-014506. HDL 1721.1/89790, https://hdl.handle.net/1721.1%2 F89790. Archived, https://web.archive.org/web/2015/math.mit.edu/bush/wordpress/wp-content/upload/2015/0/1/bush/nrev2015.pdf, PDF, from the original on June 21, 2015. Retrieved June 21, 2015. 68 Bush, John W. M. 2010. Quantum Mechanics Writ Large, https://www.inspi.nlm.nih.gov/pmc/articles/pmc2955131. PNAS 107, 41 17455 to 17456. Bibcode 2010 PNAS 107174555B, https://ui.adsabs.harvard.edu/abs/2010 PNAS 107174555B. doi 10.1073/NAS.10123999107, https://doi.org/10.1073%2 FNAS.10123999107. PMC 295-5131, https://www.inspi.nlm.nih.gov/pmc/articles/pmc 295-5131. 69 Natalie Wolkover, June 30, 2014. Have we been interpreting quantum mechanics wrong this whole time? https://www.wired.com/2014/06/ The New Quantum Reality / Wired. 70 Kudayer, Y. Fort, E. 2012. Probabilities and Trajectories in a Classical Wave-Particle Duality, https://doi.org/10.1088%2 F1742-6596%2 F361%2 F1%2 F0120001. Journal of Physics, Conference Series 361, 10120001. Bibcode 2012 JPHCS.361/2001 https://ui.adsabs.harvard.edu/abs/2012 JPHCS.361/2001 right parenthesis. doi 10.1088/1742-6596/361/1/0120001 https://doi.org/10.1088% 2f1742-6596% 2f361% 2f1% 2f0120001 71 Baggett, Jim, 2011. The Quantum Story, A History in 40 Moments. New York, Oxford University Press. Pages 76. The wave function of a system containing n particles depends on 3n position coordinates and is a function in a 3n dimensional configuration space or phase space. It is difficult to visualize a reality comprising imaginary functions in an abstract, multidimensional space. No difficulty arises, however, if the imaginary functions are not to be given a real interpretation. 72 Li, Penjiun, Sun, Yifan, Yang, Jinwei, Song, Xinbing, Zhang, Xiangdong, 2016. Classical Hypercorrelation and Wave Optics Analogy of Quantum Superdense Coding, https://www.inspi.nlm.nih.gov/pmc/articles/pmc4686973. Scientific Reports. 5. 18574. Bibcode 2015 NAT-SR, 518574L, https://ui.adsabs.harvard.edu/abs/2015 NAT-SR, 518574L. doi 10.1038/srep18574, https://doi.org/10.1038% 2fsrep18574. PMC468-6973, https://www.ncbi.nlm.nih.gov/pmc/articles/pmc4686973 right parenthesis. PMID 2668969, https://pubmed.inspi.nlm.nih.gov/2668969. 73 Backett, Vincent, Labus, Mathieu, Eddie, Antonin, Fink, Matthias, Fort, Emmanuel, November 2016. Time Reversal and Holography with Space-Time Transformations, https://www.nature.com/articles/nphysical3810 right parenthesis. Nature Physics. 12. 10.972-977 AR1415 10.01277, https://arxiv.org/abs/15 10.01277. Bibcode 2016 NAT-PH12972B, https://ui.adsabs.harvard.edu/abs/2016 NAT-PH12972B. doi 10.1038/nphys3810, https://doi.org/10.1038% 2fnphys3810. ISSN 1745-2481, https://www.worldcat.org/isn/1745-2481. S2CID 535362774, https://api.semanticchola.org/corpusid:535362774 right parenthesis. 74 Rodriguez Fortuno, Francisco J., April 3, 2023. An Optical Double-Slit Experiment in Time, https://www.nature.com/articles/S41567-023-02026-2. Nature Physics. 19, 7929-930. Bibcode 2023 NAT-PH19929R, https://ui.adsabs.harvard.edu/abs/2023 NAT-PH19929R. doi 10.1038/S41567-023-02026-2 https://doi.org/10.1038%2FS41567-023-02026-2 ISSN 1745-2481 https://www.worldcat.org/isn/1745-2481 S2CID 257945438 https://api.semanticscholar.org/corpusid:257945438 right parenthesis 75 Kastelvecki, Davide, April 3, 2023. Light waves squeezed through slits in time. https://www.nature.com/articles/D41586-023-00968-4 right parenthesis. Nature. 616, 7956 230. Bibcode 2023 Natur.616 230c. https://ui.adsabs.harvard.edu/abs/2023 Natur.616 230c. doi 10.1038/D41586-023-00968-4 https://doi.org/10.1038%2FD41586-023-00968-4 PMID 37012471 https://pubmed.inspi.nlm.nih.gov/37012471 S2CID 257922697 https://api.semanticschola.org/corpusid:257922697 right parenthesis 76 Jenkins Fa and Whitehey, Fundamentals of Optics, 1967, McGraw-Hill, New York 77. Longhurst Rs., Physical and Geometrical Optics, 1967, 2nd edition, Longman 78. Z. Anthony, 2010. Quantum Field Theory in a Nutshell, 2nd ed. Princeton University Press. Pages 2-16. ISBN 978-0-691-14034-6. 79 Fay, Jan. 2019. Copenhagen Interpretation of Quantum Mechanics. https://plato.stanford.edu/entries/qm-copenhagen/right parenthesis. Inzalta, Edward N., ed. Stanford Encyclopedia of Philosophy. Metaphysics Research Lab, Stanford University. 80 Camilleri, K. Schlosshauer, M. 2015. Niels Bohr as philosopher of experiment, does decoherence theory challenge Bohr's doctrine of classical concepts? Studies in History and Philosophy of Modern Physics. 49, 73-83. AR 14-1502.06547. https://arxiv.org/abs/1502065547. Bibcode 2015 SHPMP 49, 73C. https://ui.adsabs.harvard.edu/abs/2015 SHPMP 49, 73C. doi 10.1016/j.shpsb.2015.01.005 https://doi.org/10.1016%2fj.shpsb.2015.01.005 S2CID 2769730 https://api.semanticscholar.org/corpusid:2769730 81 Scheib, Erhard, 1973. The Logical Analysis of Quantum Mechanics. Pergamon Press. ISBN 9780080171586. OCLC 7993979091. https://www.worldcat.org/ilk/799397091. Here is no point in looking for the Copenhagen interpretation as a unified and consistent logical structure. Terms such as Copenhagen interpretation or Copenhagen school are based on the history of the development of quantum mechanics. They form a simplified and often convenient way of referring to the ideas of a number of physicists who played an important role in the establishment of quantum mechanics, and who were collaborators of Bohr's at his institute or took part in the discussions during the crucial years. On closer inspection, one sees quite easily that these ideas are divergent in detail and that in particular the views of Bohr, the spiritual leader of the school, form a separate entity which can now be understood only by a thorough study of as many as possible of the relevant publications by Bohr himself. 82 Merman, and David, January 1, 2017. Why Cubism is not the Copenhagen interpretation and what John Bell might have thought of it. In Bertelmann, Reinhold, Zeilinger, Anton, eds. Quantum Unspeakables 2. The Frontiers Collection. Springer International Publishing. Pages 83 to 93. AR 14.1409.2454. https://arxiv.org/abs/1409.2454. doi 10.1007/978-3-319-38985_4. https://doi.org/10.1007%2f978-3-319-38987-5_4. ISBN 9783319389851. S2CID 1184582559. https://api.semanticscholar.org/corpus ID 1184582559. 83 Omnes, Roland, 1999. The Copenhagen Interpretation. Understanding Quantum Mechanics. Princeton University Press. Pages 41 to 54. doi 10.2307/j.ctv173f2pm.9. https://doi.org/10.2307%2fj.ctv173f2pm.9. S2CID 203390914. https://api.semanticscholar.org/corpus ID 203390914. 84 Rosenfeld, L. 1953. Strife about complementarity. https://www.jster.org/stable/4341497. Science Progress, 1933. 41, 163 393 to 410. ISSN 0036-8504. https://www.worldcat.org/isn/0036-8504. Jster 4341497. https://www.jster.org/stable/4341497. 85 Omnes, R. 1994. The Interpretation of Quantum Mechanics. Princeton University Press. ISBN 978-0-691-03669-4. OCLC 439453957. https://www.worldcat.org/ilk/439453957. 86 Paris, Asher, 1995. Quantum Theory, Concepts and Methods. Kluwer Academic Publishers. Pages 36 to 39. ISBN 0-7923-2549-4. 87 Scully, Marion O., Englert, Berthold George, Walter, Herbert, May 1991. Quantum Optical Tests of Complementarity. https://www.nature.com/articles/3511110. Nature. 351, 6322 111 to 116 doi 10.1038/3511110 https://doi.org/10.1038% 2f3511110 ISSN 0028-0836 https://www.worldcat.org/isn/0028-0836 88 Messiah, Albert, 1966. Quantum Mechanics, https://archive.org/details/quantum mechanics 0000 mess/quantum mechanics 0000 mess. North Holland, John Wiley and Sons. ISBN 048-640-9244. 89 Frabani, Stefano, Gazzetti, Giancarlo, Grillo, Vincenzo, Pazzi, Giulio, July 1, 2015. Elastic and inelastic electrons in the double-slit experiment, a variant of Feynman's Whichway setup, https://www.sciencedirect.com/science/article/pi/s0304399115000480. Ultramicroscopy 154, 49-56. doi 10.1016/j.ultramic.2015.03.006 https://doi.org/10.1016% 2fj.ultramic.2015.03.006 ISSN 0304-3991 https://www.worldcat.org/isn/03043991 90 Rovali, Carlo, 1996. Relational Quantum Mechanics. International Journal of Theoretical Physics. 35, 8/1637-1678 AR14 Quant PH/96090002 https://arxiv.org/abs/quant PH/96090002 Bibcode 1996 IJTP 35.1637R https://ui.adsabs.harvard.edu/abs/1996 IJTP 35.1637R doi 10.1007/bf02302261 https://doi.org/10.1007% 2fbf02302261 S2CID 16325959 https://api.semanticscholar.org/corpus ID 16325959 91 Kent, Adrian, February 2015. Does it make sense to speak of self-locating uncertainty in the universal wave function? Remarks on Sebens and Carroll. Foundations of Physics. 45. 211-217 AR14 1408.1944 https://arxiv.org/abs/1408.1944 Bibcode 2015 FOPH 45-11K https://ui.adsabs.harvard.edu/abs/2015 FOPH 45-11K doi 10.1007/S10701-014-9862-5 https://doi.org/10.1007% 2fs10701-014-9862-5 ISSN 0015-9018 https://www.worldcat.org/isn/0015-9018 S2CID 1184711998 https://api.semanticscholar.org/corpus ID:1184711998 right parenthesis 92 Vaidman, Lev, August 5, 2021. Many Worlds Interpretation of Quantum Mechanics, https://plato.stanford.edu/entries/qm-many-worlds/right-parenthesis. Inzal Edward N., ed. Stanford Encyclopedia of Philosophy. 93 Deutsch, David, 1998. The Fabric of Reality, http://archive.org/details/fabricofreality0000.ut. London, Penguin. Pages 40-53. ISBN 978-0-14-014690-5. 94 Wallace, David, 2012. The Emergent Multiverse. Oxford, Oxford University Press. p. 382. ISBN 978-0-19-954696-1. 95 Philippides, C., Dewdney, C., Hilly, B.J., 1979. Quantum Interference and the Quantum Potential. Il Nuovo Cemento B52, 115-28. Bibcode 1979 SIM52, 15p. https://ui.adsabs.harvard.edu/abs/1979 SIM52, 15p. doi 10.1007/bf0274356, https://doi.org/10.107% 2fbf0274356. ISSN 1826-9877, https://www.worldcat.org/isn/1826-9877. S2CID 5357597, https://api.semanticscholar.org/corpus ID 5357597. 96 Bohmian Mechanics, https://plato.stanford.edu/entries/qmbohm/. The Stanford Encyclopedia of Philosophy. Metaphysics Research Lab, Stanford University. 2017-97. Goldstein, Sheldon, 2021, Zalta, Edward N., ed., Bohmian Mechanics, https://plato.stanford.rd.edu/archives/fall2021/entries/qm-bohm/right The Stanford Encyclopedia of Philosophy, Fall 2021 ed., Metaphysics Research Lab, Stanford University, retrieved August 14, 2023 98. Heisenberg, W., 1956. Pauli, W., ed. Niels Bohr and the Development of Physics, essays dedicated to Niels Bohr on the occasion of his 70th birthday, https://dx.doi.org/10.1063/1.30600063. Physics Today. 9. 812 doi 10.1063/1.30600063, https://doi.org/10.1063% 2f1.30600063. ISSN 0031-9228, https://www.worldcat.org/isn/0031-9228. 99 Leggett, A.J., 2002. Testing the Limits of Quantum Mechanics, Motivation, State of Play, Prospects, https://ioscience.iop.org/article/10.1088/0953-8984/14/15/201. Journal of Physics, Condensed Matter. 14. 15 R415 R451 doi 10.1088/0953-8984/14/15/201, https://doi.org/10.1088% sign 2f0953-8984% sign 2f14% sign 2f15% sign 2f201 right parenthesis. ISSN 0953-8984. https://www.worldcat.org/ISSN/0953-8984 right parenthesis. 100 Penrose, Roger, 2004. The Road to Reality, A Complete Guide to the Laws of the Universe, https://n.wikipedia.org/wiki/special book sources /0-224-04447-8, 1 Publ ed. London, Cape. ISBN 978-0-224-04447-9. 101 Hiradeki, R. 1981. De Broglie wave and its dual wave, https://dx.doi.org/10.1016/03759601, 81, 90571-5. Physics Letters A87, 395-97 doi 10.1016/0375-9601, 81, 90571-5. https://doi.org/10.1016%2f0375-9601% 2881%299057-5. ISSN 0375-9601, https://www.worldcat.org/ISSN/0375-9601 right parenthesis. 102 Hiradeki, R. 1983. Superluminal Singular Dual Wave, https://dx.doi.org/10.1007/BF02817-964. Latier al Nuovo Cemento. 36, 15509-511 doi 10.1007/BF02817-964. https://doi.org/10.1007%2FBF02817-964. ISSN 1827-613-X, https://www.worldcat.org/ISSN/1827-613-X. 103 DOS, SN, 1984. De Broglie wave and Compton wave, https://dx.doi.org/10.1016/0375-9601, 84, 90291-3. Physics Letters A102, 8338-339 doi 10.1016/0375-9601, 84, 90291-3. https://doi.org/10.1016%2f03759-9601% 2884%299029-3. ISSN 0375-9601, https://www.worldcat.org/ISSN/0375-9601 right parenthesis. 104 Mukhopadhyay, P. 1986. A correlation between the Compton wavelength and the de Broglie wavelength, https://dx.doi.org/10.1016/0375-9601, 86, 90200-8. Physics Letters A114, for 179-182 doi 10.1016/0375-9601, 86, 90200-8. https://doi.org/10.1016%2f03759-61% 2886%2990200-8. ISSN 0375-9601, https://www.worldcat.org/ISSN/0375-9601. 105 Elbaz, Claude, 1985. On de Broglie waves and Compton waves of massive particles, https://dx.doi.org/10.1016/0375-9601, 85, 90379-2. Physics Letters A109, 1-2 7-8 doi 10.1016/0375-9601, 85, 90379-2, https://doi.org/10.1016% 2f0375-9601% 2885% 2990379-2, ISSN 0375-9601, https://www.worldcat.org/isn/0375-9601. Further reading Al-Khalili, Jim, 2003. Quantum, A Guide for the Perplexed. London, Weidenfeld and Nicholson. ISBN 978-0-297-84305-4. Ananthaswamy, Anil, 2018. Through Two Doors at Once, the elegant experiment that captures the enigma of our quantum reality. Dutton/Penguin. ISBN 978-1-101-98609-7. Feynman, Richard P., 1988. QED, The Strange Theory of Light and Matter, https://archive.org/details/KED-Strange-Theory 00 Princeton University Press. ISBN 978-0-691-02417-2. Frank, Philip, 1957. Philosophy of Science. Prentice Hall. French, A.P., Taylor, Edwin F., 1978. An Introduction to Quantum Physics. Norton. ISBN 978-0-393-09106-9. Green, Brian, 2000. The Elegant Universe, https://archive.org/details/elegantuniverses0000 Vintage. ISBN 978-0-375-70811-4. Green, Brian, 2005. The Fabric of the Cosmos, https://archive.org/details/fabric-of-cosmos P00 Vintage. ISBN 978-0-375-72720-7. Gribben, John, 1999. Q is for Quantum, Particle Physics from A to Z. Weidenfeld and Nicholson. ISBN 978-0-7538-0685-2. Hay, Tony, 2003. The New Quantum Universe. Cambridge University Press. Bibcode 2003 NQU Book, H. https://ui.adsabs.harvard.edu/abs/2003 NQU Book, H. ISBN 978-0-521-56457-1. Sears, Francis Weston, 1949. Optics. Addison Wesley. Tipler, Paul, 2004. Physics for Scientists and Engineers, Electricity, Magnetism, Light, and Elementary Modern Physics, 5th ed. W. H. Freeman. ISBN 978-0-7167-0810-0. External links Double-slit interference lecture, https://youtube.com/watch, v=1 RYF72PXVKS, by Walter Lewin of MIT Interactive Animations Huygens and Interference, http://www.acoustics.salford.ac.uk/feschools/waves/diffract3.htm right single particle experiments website with the movie and other information from the first single electron experiment by Murley, Missiroli, and Pazzi. http://el-espellel-bellota-bella-bella-fissica.beo.imm.cnr.it/english/index.html. Movie showing single electron events build up to form an interference pattern in double-slit experiments. Several versions with and without narration. File size equals 3.6 to 10.4 MB. Movie length equals 1 minute and 8 seconds. https://web.archive.org/2016110442639/http://www.hitachi.com/rd/research/m/movie.html. Freeview Video Electron Waves Unveil the Microcosmos, a Royal Institution discourse by Akira Tonomura provided by the Vega Science Trust. http://www.vega.org.uk/video/program me/66. Hitachi website that provides background on Tonomura video and link to the video. https://web.archive.org/web/20110114170600. http://www.hitachi.com/rd/research/em/double-slit.html right parenthesis hydrodynamic analog single particle interference observed for macroscopic objects. http://www.physicalorg.com/news78650511.html. Pilot wave hydrodynamics. Supplemental video. http://www.annualreviews.org/doi/pl/10.1146/anuref-fluid 0108140/0145006. Through the Wormhole. Yves Couder explains wave/particle duality via silicon droplets. https://www.youtube.com/watch V equals W9YWV5DQSKK. Computer Simulations Java Demonstration of Young's Double-Slit Interference. http://vsg.quasihome.com/interref.htm right parenthesis a simulation that runs in Mathematica Player, in which the number of quantum particles, the frequency of the particles, and the slit separation can be independently varied. http://demons-tirations.wolfram.com/wave particle duality and he double slit experiment right parenthesis retrieved from https://en.wikipedia.org/w/index.php title =double-slit_experiment and olded =11746470019